What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today, we are looking at a real life, not real life, that's silly. Everything's real life. We're looking at an example of a scenario in which we can verify the conservation of momentum and check for elasticity. We've done some simulations, but here today I asked you to go ahead and devise a plan. How could I use some tools to verify momentum is conserved in a collision and then check to see the elasticity or inelasticity of a collision? So here's what I gave you. I went ahead and I gave you two smart carts with a round spring on the front. I gave you a second cart with some masses that you could also put on the cart here. And I asked you to collide these two objects on a metal track. I gave you a track like this, and I said, okay, verify that when these two things collide, momentum is conserved, and check to see if it's elastic or inelastic. I mean, check it out. They bounce off each other, so that's pretty neat. So I asked you to go ahead and devise me a plan. What data will I need to take in order for us to go ahead and verify this? So before I can go ahead and begin my procedure, I need to come up here and brainstorm what are some things that I should be doing. First of all, happy Monday. Thanks, Mira, for writing the happy Monday. But what are some things I might need in order for us to go ahead and check to see if momentum is conserved? Well, momentum we know as its own quantity is mass, the vector quantity of mass. Momentum is mass times velocity. And these are vectors, so direction is going to be important here. So I have to think about this. Before the collision and after the collision is what I'm thinking of. The momentum initially should be equal to the momentum finally. And this is what we're looking for. We're trying to verify this. So if we think about this scenario, we would think that there's momentum in the yellow cart. Momentum in the yellow cart initially plus whatever momentum is in the blue cart initially should be equal to the momentum in the yellow cart after a collision plus the momentum in the blue cart after the collision. Again, all vectors, so direction is going to matter. So I need to think about, okay, what makes up momentum? I guess the mass of the yellow cart is going to be important. The initial velocity of the yellow cart is going to be important. The mass of the blue cart, its initial velocity is going to be important. And then after the collision, I'm going to need to see these quantities also to verify whether or not momentum is conserved. So if I think about creating a data table from this, this is what I need to know. What are some things I'm going to need to find out? Well, there's going to be a yellow cart, and there's going to be a blue cart. And in order for me to get what I need to verify this expression, I'm probably going to have to know mass of both. I'm probably going to have to know initial velocity for both and final velocity for both. Now, the interesting thing is that the mass won't change for either object, so I don't need to know those things. But there's really, 6 variables here. Mass of both carts, and then initial and final velocities for both carts. From here, from this data table, from this equation, I should be able to kind of generate a procedure. Our procedure might be set the two carts up, slide them together, roll them together, have them collide, and take data on their initial and final velocities. It's a good thing that we have our smart carts here, because the smart carts I can connect to my computer, and when they're connected to my computer, they will actually give me data on velocity before and after the collision. That's why we pay so much money for these really smart carts. So that's exactly what we're going to do. I'm going to back you up. You can see the lights are blinking. That means they're connected to my computer. And when they are, I'm going to go ahead. I'm actually going to slide the heavier one at the blue one. I could go ahead and slide the lighter one, but I've increased the mass of this to make sure there's pretty obviously a difference in initial momentum of this cart and the final momentum here. I don't want any kind of weirdness to happen, so I made sure to make sure that these masses are different. I'm going to go ahead and extend both plungers. That way, if a collision happens in the back end, it will bounce. And let's go ahead. 3, 2, 1. I'm going to send this cart towards this cart. And there we go. Bounces back off, and they're going to bounce back this way. That's it. They're connected. I hit collect. I'm collecting data. I just want the initial velocity before the collision. It collides, and the velocity after the collision. One kind of nuance to this in the real world here is that friction does exist. So I don't actually want the speed of the car over here, or over here. I need to make sure I get the speed of the car right before the collision, because the car is going to slow down a little bit before the collision. So if you're taking this data on your own or in the classroom, be sure you take the data right before the collision and then immediately following the collision, because there is friction before, after, and during. This is weird that this collision takes place over a distance over time because they squish. Friction doesn't stop existing. So let's make sure we get data right before the collision and right after the collision. Okay, so we can look and go like right now and right now. Those 2 points are the data points we want, and I've got them on the board. Let's go check this out. The data we gathered from that exact experiment is right here. So here's our data table, and here are the measurements we got right from that those smart cards. Here they are. You should be able to now, on your own, go out and verify whether or not momentum was conserved using this expression right here. If it was, fantastic. It should be, at least it should be really, really, really close, because even though there's friction, there's only a little bit of friction. So it should be really, really, really close to being conserved. The next question that I asked was to check and see if the collision was elastic or not. And the big idea here is that like they bounce off. So yeah, it's elastic. Wrong. That's not what we mean in physics when we talk about perfectly elastic collisions. Elastic collisions, yes, there's bouncing, 100%. The English definition of the word elastic means to be bouncy or to regain its shape, something like that. But that's not what I'm looking for here in the classroom. Elastic, as a definition, or perfectly elastic, means the kinetic energy of the collision initially should be equal to the kinetic energy of the collision after. I'm looking to see, is kinetic energy conserved before and after this collision? This is the second part to this experiment. And so in order for us to think about this, I need to think which carts were moving. Well, there's kinetic energy of the yellow cart plus the kinetic energy of the blue cart. Should be equal to the kinetic energy of the yellow cart. This is initial, this is final, and this is final. Kinetic energy does not have a direction, so I'm not too concerned about the direction these carts are moving in, just the magnitude of their speed squared. And if I think about the equation, well, this wasn't moving to begin with, so that's not there. But it would be the mass of the yellow cart times the initial speed of the yellow cart squared. This should be equal to 1/2 mass of the yellow cart, final velocity of the yellow cart, plus mass of the blue cart, final velocity of the blue cart squared. This is my second check for verification. If these two things are equal, if both sides are equal, it's definitely a perfectly elastic collision. If they are not, then energy was lost somewhere in the collision, and that is most typically the case. Most typically, these collisions are not elastic, but you go verify it. All right? So we've gone ahead, it gave you a task, verify conservation of momentum. Through our equation and our understanding of what that means, we were able to generate a data table. From the data table, we were able to then decide how I should use my tools to go ahead and collect that data. Then, once we collected the data, we were able to go back, use the equation we set up to verify conservation of momentum. Next, we fixed our definition or relearned our definition of an elastic collision, used that same data and our understanding of conservation of energy expressions to then verify whether or not this collision was elastic. I'm not going to do the math for you. Do the math at home. You're the one that missed class. Go do the math at home. Verify whether or not momentum is conserved. Verify whether or not energy is conserved. If you have questions, leave them in the comments. Send me an email. Until next time, see ya!